Okay, we're going to work on 7.5. This is a really fun lesson. We're doing operations with radical expressions. And to be honest, we've already used this product property of radicals a million times. It simply says if you have a radical and you're multiplying two things, you can break it up into two separate radicals. And vice versa, if you have two separate radicals, you can go ahead and put it that in your multiplying underneath each of, you're multiplying two radicals, you are allowed to go ahead and multiply the two numbers under one radical and combine them to make a really nice number when it's convenient. Similarly, you are allowed to break up a radical if you are dividing. You can break them up into separate radicals. We've done this before many times. So I know that we've taken the square root of things like 25/4 before by taking the square root of 25 and dividing by the square root of 4 and getting 5/2. I know we've done this when we've completed the square. So this is not really new. Okay, conjugates are simply, let's see, it's binomials. That is something like something plus something. And its conjugate is when you have the same two numbers, but the sign in the middle is different. The sign connecting them is different. And we've talked about conjugates before. The word came up before when we had a complex number like 3 plus 2i. Its complex conjugate was 3 minus 2i. So the two terms are the same, but the sign connecting them is different. So the word conjugate is used today a little bit later, and so we wanted to make sure you knew what that was. Okay, remember all your answers have to be in simplified form, and that means that first of all the index has to be as small as possible, and you might not know what that means right now. It's this number down here, remember, and as we're working problems you will see that I manipulate it to make sure that all the indices are as small as possible. The radicand contains no factors other than 1 that are nth powers of an integer polynomial. What does that mean? I can't say what's the square root of 32 when I know that the square root of 32 is really the square root of 16 times 2, and the square root of 16 is a second power of an integer. So that was really 4, and this is square root of 2. So the square root of 32 would not be simplified because there was a perfect square in it. Think of it that way, that you could take the square root of. So that should be common sense. The radicand cannot contain any fractions. You can't say your final answer is a square root of 3/5. I will mark that wrong. What you're going to have to do in this case is make it the square root of 3 over the square root of 5, and then your denominator cannot have a square root in it, a radical, so you have to multiply the top and bottom by the denominator, which is square root of 5. So this is like multiplying by 1. So what you would end up with is the square root of 15 over, what do you think? 5. Very good, because this equals the square root of 25. And last but not least is what I just mentioned. You can't have a radical in a denominator. Any of these things will result in many points taken off on a test, because you should know when something is in simplified form, and that's basically that's one of the things I am, not basically, but that's one of the big things that I am testing you on also. So let's look at number 6. They ask us to simplify. Okay, what I'm going to do first is combine them into one radical. Now go ahead and write the problem. Let me pause for just a second. I'm doing number 6. 4 radical 5a to the 5th times radical 125a to the 3rd. So I'm going to first say, well, when I'm multiplying, first of all, I multiply the 4 by the implied 1 that's over here. So I still have 4 on the outside of the radical, but what I have now is 5 times 125. Is that 625? Probably. That's 625. And then I have a to the 5th times a to the 3rd, which is a to the what? Hope you said eighth. Remember, when you're multiplying powers, you add. the exponents. Okay, now I wonder, is 625 a perfect square? Well, we'll take the square root of that last answer in our calculator. We get 25. So this equals 25. And what's a to the 8th but taking the square root? Remember, the root is implied to be a 2, so 8 divided by 2 is the 4th power. Now don't forget what I was mentioning before. If I have even, even, odd, I put an absolute value sign on it. But I don't have that situation because my exponent of my answer is not odd. I had even, but not odd. So I have 4 times 25, which is 100a to the 4th. So this would be a final answer. I did not, what's the word? Oh, like when you break a law. I did not, well, I don't know. I didn't break any of these rules up here in simplification. All right, let's do it again with number 8. The problem is the 4th root of 3x to the 3rd, y to the 2nd, times the 4th root of 27xy squared. So when I combine them, I still have the 4th root, which reminds me, if this was the 3rd root, I wouldn't be able to combine them. Didn't think of that. 27 times 3 is 81. X to the 4th, y to the 4th. Remember, you are adding exponents. What number times itself 4 times gives you 81? Well, if you knew that 3 to the 3rd was 27, this is another 3, hopefully you realize that would be 3. So this is 3. Of course, you could have used your calculator. X to the 1, y to the 1. Do we need absolute value? We have an even, odd. Yes, we do. And even, oops, sorry. And then we have even, odd. So we need an absolute value sign on both the x and y. And if we need it on both, we could go ahead and put it between, encompassing both of them at the same time. Wow. Oh, this one's super fun. When you have adding and subtracting, just like with variables, you can't actually do them unless the variables were the same. Well, this is like saying 4x plus 3y, because these two are different, minus z. Well, you can't actually combine them because they're not like terms. So what we're going to try to do is make them like terms. All right, go ahead and write the problem number 10. 4 radical 40 plus 3 radical 28 minus radical 200. I'm going to break 40 up into, I like to use a tree method where I break it down into its prime factorization. So keep breaking down the factors until you can't do it anymore. And all you're going to do is take the last numbers you've gotten. You're not going to look at the 4, the 10, and the 40 anymore. You're only going to look at the ones left over. This is how I do it. If this is the square root, which of course it is because there's no number there, I am looking for 2 numbers that match. If 2 numbers match, I'm allowed to pull one of them out because it's kind of like taking the square root of 4, basically, is what I'm doing. So, you know what? I'm going to write it out in case you don't understand what I'm saying. This is a combination of a method you might have learned and the tree method. I call it the tree method. This would be 4 times the square root of 4 times the square root of the leftovers, 2 times 5. So that's really 4 times square root of 4 times the square root of 10. But see how square root of 4 is actually just 2? That's why when I circle 2 numbers, I only pull 1 2 out. Then I'm left with the square root of 10. So this turns out to be 8 square root of 10. Now let's do the same with 3 times radical 28. 28 is 2 times 14 and 2 times 7. So again, if there's 2 numbers that I can circle, and the reason I picked 2 numbers to circle is because there's an implied 2 here. I hope later we get to do it, yes, with more. Yes, that's going to be fun. Okay, so what I have is the 3 that's already outside times 2 that I'm pulling outside times the square root of what's left over, 7. So I think of this as 6 times the square root of 7. Now these still are not like terms, so I'm not going to be able to combine these two, but I still have hope for that square root of 200. All right, let's break 200 down. Now, to be honest, if I do 200 is 2 times 100, and I notice that this is 10 times 10, I don't have to continue going down. I could just say, hey, I have two numbers that match, and that's going to be 10 gets pulled out and radical 2. Let me show you. Oh my gosh, I guess I erased my writing. What happened here? Let me show you the check for this. What you do for all these problems is square this number, you get 100, and then multiply by this number, you get 200. That won't really work for this because we had a number outside, but basically right here, 2 squared is 4 times 7. 2 squared, right here I am, 2 squared is 4 times 10 is 40. So that's your little check in case you are unsure about how you rewrote your radical. So, oh my goodness, I have none of these matching. Therefore, this is my simplified answer. Remember, this was not allowed, even though I can't combine them, I can't leave my answer like this because there was a perfect square in each of these radicals. All right, let's try 30. Hopefully we get somewhere with 30. We get to do a little more. My goodness. Okay, let's break down 90. 90 is 9 times 10 and 3 times 3 and 2 times 5. So since I can pull out a 3, and I already have a 3, I have 9 outside, left over radical 10, plus 4 times radical 20 will be 2 times 10 and 2 times 5. Notice that even if you did 4 times 5, you would have gotten 2 times 2 times 5. You always get the same prime factorization no matter how you do it. So this is going to be 2, and then this will be, whoa, left over radical 5. 162, let me erase this. 162, I know it's even, so I'm going to divide out a 2, and that gives me 81. And right away, I know that's 9 and 9. I can just circle the 9s, but just to show you how it works, if I went further, I can circle 2 3s, so I pull out a 3. I can circle another 2 3s, so I pull out another 3. You see how that's the same as pulling out a 9? Then I'm left with square root of 2. So what I have now is 9 radical 10 plus 8 radical 5 plus 9 radical 2. Okay, I guess I have no like terms again because all of the numbers inside the radical are different. So I have to leave it like that. That's the simplified form. Yippee! We get to FOIL now. This is super duper fun. I wanted to make sure I didn't miss the screen. I'm simply going to FOIL number 12. Let me give you a second to go ahead and write it. Okay, I'm going to multiply 8 radical 3 times 8 radical 3. Well, what I do is multiply the 8 times 8, and that's 64. Radical 3 times radical 3. Do you realize that's the square root of 3 squared, so the 2's cancel, so that's just 3. Or you could think of it as that's the square root of 9. Then we multiply this times outside. The outside times outside. And since it's positive times positive, it's positive. 8 times 2 is 16. Now, square root of 3 times square root of 2 is square root of 6. Okay, now we take the middle term and multiply by both. So the first one will give me negative 2 times 8 is 16. Square root of 2 times square root of 3 is square root of 6. Last times last, positive times negative is negative. 2 times 2 is 4. Square root of 2 times square root of 2 is 2. Let's simplify. 64 times 3. I hope you always have a calculator next to you when we're doing math. This is 192 plus 6. Do you realize something? I have plus 16 radical 6 and minus 16 radical 6. Those actually go away. So I'm actually left with 192 minus 8. And of course I can do that. It's 184. Now, how did I get rid of all my radicals? I want you to notice that this was the conjugate. Notice these two numbers are the same. These two numbers are the same, but the signs in the middle were different. So when you multiply by conjugates, the radicals disappear. Oh my gosh, that's going to be a very handy thing to do to get rid of radicals. So notice that. All right, let's do number 40. Those are not conjugates. We'll probably end up with some type of radical. We don't know. Let's see. When I multiply the first one times the first, I get 6 times 2 is 12, times the square root of 3 times 16, which is 18. I have a feeling that simplifies. I'll do that in the next step. 6 radical 3 times 3 radical 8 is a positive, because it's positive times positive. 6 times 3 is 18, and then square root of 3 times 8 is 24. Now, inside times inside. Positive times positive is positive. 5 times 2 is 10. 2 times 6 is, hold on, 12. 5 radical 2. Okay, so positive times positive is positive. 5 times 3 is 15. Square root of 2 times square root of 8 is square root of 16. So let's break 18 down. 18 is 2 times 9, and 9 is 3 times 3. So we can pull out a 3. So we have a 12. Now we're going to multiply it by 3, and we're left with a 2. Square root of 24 is 4 and 6 and 2 and 2 and 2 and 3. Pull out a 2, and we're left with square root of 6. Radical 12. I'll try to slow down so you can be a little bit ahead of me. First square root of 16 is just 4. So now we multiply these and get 36. I think that's 36 too. Okay. Let's look at these. These are not like terms because they each have a different radicand, so we can't combine them, but this would be the simplified answer. Okay, let's go to 16. The problem with 16, the reason it's not simplified, is because it has a radical in the denominator, and we can't have that. So what we have to do is, the only thing we can do is multiply by something equivalent to 1, because multiplying by 1 is something that does not change the value of any quantity. So I'm going to multiply by the conjugate of the denominator. Multiply top and bottom. multiply top and bottom by the conjugate of the denominator. So what's the conjugate of the denominator? Remember, the two terms are the same, but the sign between them is the opposite. Now, in order to make this value right here equivalent to 1, I have to have the numerator to be the exact same quantity, right? Isn't 156 over 156 equal to 1? Yes, it's because the numerator and the denominator have the same value. So what do you think we're going to do now? We're going to FOIL, top and bottom. Oh, it's so much fun. I can't wait to dig in. So that's going to be 6 radical 3. 6 times negative 4 is negative 24. Well, negative square root of 3 times positive square root of 3 is negative square root of 9. I could have just written 3. Negative square root of 3 times negative 4 is a positive. It's going to be 4 radical 3. The bottom, remember, we should be able to get rid of the radical when we do this. Square root of 3 times square root of 3 is 3. Positive times negative is negative 4 radical 3. Positive times positive is positive 4 radical 3. Oh yes, those are going to cancel. 4 times negative 4 is negative 16. So what do we get? On the top we have 6 radical 3 plus 4 radical 3. When I add those I get 10 radical 3. It's just like adding 6x plus 4x. It's 10 radical 3. Then we have negative 24 and minus square root of 9 is really 3. So I'm going to simplify that in the next step. The bottom, I have 3 minus 16. Remember that 16 and the negative go together. This negative sign went with this number. Some people get confused with where their signs are placed. So in the next step, I'll say this is 10 radical 3 minus 27 over negative 13. Now, they might leave it like this, and this is good as long as there's not a common factor. But what I would suggest doing, so you can see if it reduces, is make this 10 radical 3 over negative 13 and realize that 10 and 13 have nothing in common. So it is simplified. And then we have minus 27 over minus 13. So that's really plus. So we have 10 radical 3 over, or negative 10 radical 3 over 13 plus 27 thirteenths, which doesn't reduce. This is easier to see that they need to reduce each one in order to simplify. All right, try number 44 without me, and then I'm going to, and then hit play again. All right, so let's multiply the top and bottom by the conjugate of the denominator. So it's square root of 5 and square root of 2, but instead of plus, it's minus. And then we multiply the top by the same. So when I distribute, I get 2 square root of 10 minus 2 square root of 2 times square root of 2 is just 2. Plus 2 square root of 5 times square root of 5 is 5. Plus times minus is negative 2 square root of 10. 5 minus square root of 10 plus square root of 10 minus 2. So we get 2 radical 10 minus 4 plus 10 minus 2 radical 10. Hey, those are going to cancel. I didn't catch that. Then we get, well, these cancel. About that. So we have 5 minus 2. So we have negative 4 plus 10, which is 6, over 5 minus 2, which is 3. This is equal to 2. Who would have seen that? Well, to be honest, I've had really smart students notice something. Watch this. Could I have pulled a 2 out of the top, undistribute, and get square root of 2 plus square root of 5? Then what's the bottom equal to? Hey, that's the same as square root of 2 plus square root of 5. Since these quantities are identical and we're multiplying, we could have canceled those. But it's okay. Good practice. All right, let's look at these. I'm going to show you the tree method when you're trying to take the cube root of negative 54. I'm going to first rewrite it this way because sometimes the negative gets me confused. So what I'm going to do is this. I'm going to make this the cube root of negative 1 times 54 times x to the 6, y to the 11. Just for demonstration purposes, I think I'm going to break it up one more time. The cube root of negative 1, the cube root of 54, the cube root of x to the 6, the cube root of y to the 11th. I don't have to worry about my little absolute value signs because I don't have even, even, odd. My root is an odd number, so I don't have to worry about that. So what's a cube root of negative 1? What number times itself 3 times gives me negative 1? Well, it's negative 1. So that one's easy. Now let's talk about the cube root of 54. Let me show you how I do it. I'm going to make a tree again, and I'm going to break it down into the prime factorization. Well, I know 54 is 9 times 6, and I know that 9 is 3 times 3, and 6 is 3 times 2. Well, guess what? Guess what? Now that the root is 3, I need 3 numbers to match in order to pull one out. So I propose this is going to be equal to 3 times the cube root, still, you always leave the root the same, of 2. Now, let me show you over here why. Because isn't this the same as the cube root of 27 times the cube root of 2? Why? Because 27 times 2 is 54. And what's the cube root of 27? What number times itself 3 times gives us 27? Oh, it's 3. That's right. That's why I needed to circle 3 numbers that matched in order to pull one out. So then we're left with the cube root of 2. Now what about this? Using our shortcut method, 6 divided by 3 is 2. This is x squared. And this one, now this one's weird. You're going to have leftover. So think about it. If you divide 11 by 3, you're not getting a whole number. So think of it this way. The cube root, wouldn't you say this is the same as the cube root of y to the 9th times the cube root of y squared? How did I pick 9? 9 was the biggest multiple of 3. That was less than 11. So for this one, it's going to give me y to the 3rd. And then this one is like too small to actually take the cube root of. It's like taking the square root of 5. The number's too small to take the square root or take some number out. So I'm left with the cube root of y squared. So what's my answer? Let me highlight. I have negative 1 times 3, which is negative 3, times x squared y cubed. First, I have negative 3x squared y cubed times the cube root of 2y squared. I multiplied 2 and y squared. They were both under the same cube root, so I combined them. So this would be my answer. Now, if you didn't understand this part about the cube root of y to the 11th, let me show you another way to think about it. Isn't this the same as the cube root of y to the third times y to the third times y to the third? That's 9. Y to the second, 10, 11. And don't you know that that's the same as the cube root of y to the third? And remember, the third root and the third power cancel, and that's just y. Third root of y to the third, third root of y to the third, third root of y squared. Similarly, bloop, 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 bloop. This is equal to y, this is equal to y, and this is the cube root of y squared. So this turns out to be y to the third power, and that's what we got up above. Let's try 48. Okay, fourth root of 48. Let's break 48 down. I'll try to go slowly. Again, I have to always remind myself. Do I have how many numbers? 4. That I can circle? Yes. How many times do I pull that out? Just once. I pull out 1, 2, and I'm left with the fourth root of 3. Now, a to the 9th to the 4th. It's really, remember, maybe I'll do an intermediate step. Oh, no, I can do it here. It's the fourth root of a to the, what's the biggest exponent that's divisible by 4? Not divisible by 4. Yeah, multiple of 4. That's less than 9. Isn't it 8? So isn't a to the 9th equal to a to the 8th times a to the 1? Sure is. Then I'm left with the fourth root of b to the third. 3 is too small to even simplify this. 3 over 4 is less than 1. So I can't do it. And then what about this? 16 divided by 4 is 4. So c to the fourth. Now I don't have a radical there. I took it out. So what I have so far is 2c to the fourth. This turned out to be a squared. So I'm left with the fourth root of 3ab cubed. So I would write it in alphabetical order, changing the a and the c. Make sure you spread it out, write it really neatly, so I know that there's a gap here basically, or that, you know, this 4 is not the same as this 4, and they don't all blend together. You want to write this very neatly and make sure your root is small and fitting into this little crevice, all those things. So writing this a little large and spread out will really help. Okay, how many more problems? The Lord have mercy, this is a lot. Okay, there's so much fun. I mean, I love to do them quickly. I hope you get to the point that you can do them quickly. Okay, now the bottom of number 52. There is no complex or conjugate for it, because this is why. The radical goes across the whole bottom, and that means this is just one quantity. It's kind of like 4 over square root of 3. I just multiply the top and bottom by square root of 3, and boom, I'm going to have this fixed. This is the same thing here. When it's this case where you have only one radical and a quantity underneath, you multiply it times itself. So I'm just going to multiply the bottom and top by the bottom. Why? Because remember, when I do this and multiply it to itself, these two cancel. So it gets rid of the radical. So the bottom just has x squared minus 4, which is great. There's no more radical left. Now on the top, I get x minus 2 times the square root of x squared minus 4. Now it's really important to understand that x minus 2 is one quantity, and so I'm going to put them in parentheses, and this is multiplication. Why did I do that? Because I didn't want you to think that only the 2 got multiplied by this, but both the x and the minus 2 would have to be multiplied by that radical. Now I can continue again, and do you know why? Because the bottom factors. Remember, you can't do anything with this because you cannot break this up into separate radicals. You can only do that when you're multiplying and dividing. But the bottom, guess what? The bottom factors into x and 2 and 2 and plus and minus. So these two factors cancel. And remember, I can cancel because I am multiplying those terms. So I am left with the square root of x squared minus 4, which does not simplify, over x plus 2. I have no radical in the bottom. And I have no radical in the bottom. Okay. Same with 53. Try 53. It's the same process. Let's look at that one. I'm not sure if it will simplify like we did over here with the factoring, but let's just multiply top and bottom by the bottom. That gives us square root of x over square root of x squared minus 1. Remember, this does not simplify. Over x squared minus 1. These actually don't factor. The bottom will factor, but to be honest with you, it's going to be x plus 1, x minus 1, and that doesn't factor with anything on the top. So we don't need to factor it because it doesn't result in any canceling. Oh, okay. So let's talk about rationalizing a denominator. Remember the example, let's see, something like 2 over the square root of 5. To rationalize the denominator, this is really important, rationalizing the denominator. Let's do a couple problems. It's not bad when the root is 2, but I'm going to show you how to do it when the root is something bigger. It's really kind of cool. We're going to multiply the top and bottom by the square root of 5. The top gives us 2 times the square root of 5, and the bottom gives us just 5. That was the whole reason I picked square root of 5, because it's the square root of 25 now, which just equals 5. But what happens when there's a root here, like the third root or something? I'm going to show you what will happen. Here we go. This is so much fun. Okay, I need to get rid of the radical in the bottom, but to be honest with you, I can't get rid of the third root unless inside is something cubed. So this is what I have to do. I have to multiply the top and bottom by the perfect number, and it's going to be the cube root of something, so that now I do have the third power in it. And as I work it, I think it will make more sense as I do it. So this is 10. Do you see? If I multiply by another 2 tens, I'll have 10 times 10 times 10, which is 10 to the third. And then when I take the cube root of 10 to the third, it gives me 10. Cool. I'm going to multiply top and bottom by the cube root of 10 squared. Now, what is 10 squared? It's really the same as 100. So on the top, I'm just going to say 100. Now, down on the bottom, I have x. Wow, I wish it was x cubed, because then x cubed, cube root, that would just equal x. That would be so wonderful. How can I make it x cubed? Well, I'll multiply by another 2 x's. So I have x times x times x, which is x to the third. In the next step, it might be more obvious. So I have to be fair and multiply the top by x squared. How many more z's do I need? Hope you said 2. So I'm going to multiply the top and bottom by that same quantity. Now, let me show you what happens to the bottom, and this is the whole reason I did it. Now I have the cube root of 10 to the third power, x to the third power, and z to the third power. And I hope you see in the next step, all I'm going to get is 10x z. That is beautiful. No radical left. But the top, I left myself a pretty decent mess. I have the cube root of 36 times 100, so it's 3600. X times x squared, that's x cubed. Y squared, that's y squared, and z squared, z squared. So I'm going to break that 3600 down using a tree. I'm going to say that is 36 times 100. That's 6 and 6 and 10 and 10. Now, how many numbers do I need to match to pull one out? Well, because it's a cube root, I need 3. So I don't have 3 numbers that match yet, so I have to keep breaking it down. 3 and 2 and 3 and 2 and 2 and 5 and 2 and 5. Now, do I have 3 numbers that match? Yes, I do. I have a 2 and a 2 and a 2. And I guess that's it. So I can pull out a 2, and I'm left with, oh wait, let's look at the variables. I have x to the third raised to the third power, so it's just x. And I have z squared, and y squared, not enough to pull out. So I'm left with the cube root of 3 times 3, 9, times 5. I'm going to do this in my calculator. 9 times 5 times 2 times 5, which is another 10, so that's 450. Again, the check for this would be, what's 2 to the third power times 450, and I'm getting 3,600, so I'm glad about that. We still have a y squared and z squared. Now take a glance at this final answer. Do you think there's something I can do to, to simplify it more? Yes, because these are all multiplication, I am allowed to cancel. 2 goes into 5 once, and the x's will cancel. I'll scratch those out. So the top I get 3 radical 450, y squared, z squared, and on the bottom I get 5z. No radicals left. See why we need to practice this a lot? It's going to take a lot of practice to get really good at this. All right, go ahead and try these problems if you want, and I will do them really quickly in a minute here. I'll do them silently. Have a great night, guys.